Hi, welcome to the chapter 3 Arithmetic for Computers. And in this lecture, we will discuss floating points. And there is, before we get into floating point, using integers or fixed point arithmetic has one major issue. And let's go to the whiteboard here. And obviously, people could represent numbers from 0, 0, 0, 0 using 4-bit representation all the way to 1, 1, 1, 1. In this case, we are representing integers, okay? We can choose to have them signed and unsigned, and that's not the point here. The point is that later on, people felt the need that they need to represent fractions, and what they decided to do, they said, okay, we'll split this range into a fixed point in the middle, and I'll have two numbers for the integer part and two numbers for the fraction part, and this is what referred to as a fixed point. And obviously this had worked for some time, but then the people realized that there is limited precision and and limited range. Okay, so with this range, so I cannot represent numbers to very fine precision or very large range. And that's when people start thinking that this fixed point approach is not working, and we have to go to a floating point approach. And in the floating point, basically what we do is that we represent the number as such: 1 dot something, and I'm talking about the binary number, times 2 to some kind of exponent. Now somebody might say, well, what if the number, for example, let's say for example I'm representing number 5. Okay, so number 5 in binary is 1 1. So how do I insert or confirm to this format, which is the floating point format? So we say, well, that's easy. You have to write a 1 first, decimal point second, then 0, 1, and multiply. So how many positions I moved? So I moved this decimal point 2 positions over here. So I say 2 to the 2. Okay, and this is 2 to the 2 will is equal to 5, and this is what we refer to as the floating point format. You have to have the number 1 decimal, okay, and then a fraction. And how to achieve this? You play with the exponent here. Okay, so with that, let's go to the slides. Okay, and here in the slides what I have is let's see, um, in the slides here, he said that this is the floating point notion and the need for it. We will talk about later on about the denormalized number, but he noticed that the notion of normalized is that you have a digit and a decimal point. Of course, in decimal number, the digit, this can be anything from 1 all the way to 9, something non-zero. Therefore, this is not the format, and this is not the format of normalized number. In binary, since I have a digit either 0 or 1, I must have a 1, a fraction, and this decimal point, and this exponent here raised to the power this exponent. Okay, now of course in programming, these floating point number can be of type of float or double. And there is a standard IEEE, which is specified single IEEE standard, which is specified single precision, double precision, quadruple precision, and more even. But we're going to focus on single precision, and we also mention and pay attention to some of the double precision examples. And in fact, once you understand the single precision, you just kind of extend the numbers and the ranges of the numbers to other types of precisions. Okay, so basically, how we save this format in the memory, the most significant bit is S here indicates for me the sign. So if S is 0, it means that this number is positive. If S is 1, this number is negative. Now, then I have the exponent, okay, part, which is in the case of single bit 8 bits, I'm sorry, single precision. In the case of double precision, it is 11 bits. Then I have the fraction here, which is in the case of single precision 32 bits, and in the case of double precision 52 bits. If you add up how many bit number, you'll find that this, for single precision we have 32 bit, and we for double precision we have 64 bit. Okay, so the 32 bit is the space needed to save a single precision floating point, and the 64 bit is the space needed to save double precision. Now you can kind of now understand that the double precision, which offers more precise and larger range, requires more memory, okay, and more processing, and more and larger adder, floating point adders and dividers and multipliers. So now you can see that there is a price with the extra precisions that we are offering in double precision. Now, how to compute the value of this number? So what I do is that I take this fraction and I add to it a 1. Why 1? Well, you see, typically the normalized number is something like 1 point something xxxx. That's the normalized number. This number 1 is not saved in the memory because it's always there. Why waste a single bit? So we take this x and save it in the memory. Now, when we compute the value of the floating point number, okay, we take this fraction and we add to it the one that we did not save, so that we recover the numerical value of the significant. Now, in terms of the exponent here, we take this exponent and we subtract from it a bias. What is this bias? You see, the exponent, when we save it in the memory, the exponent value can be of negative or positive. And what we do, because we would like always to think of the exponent that is being saved in the memory as positive value, we add to it a bias. And when we want to recover its true value, we subtract the bias. So when we save the exponent in the memory, we add the bias. When we do the computation, we subtract the bias. To be honest, it's one of those things that irritates me about the IEEE format. But here, that's the standard, and we have to abide with it. Okay. So the question is, what is this? What's the value of this bias? Well, the value of this bias is 2 to the power number of bits minus 1 minus 1. So in the case of single precision, it is 127. In the case of double precision, it is 1023. Okay, and let's take a look at here at some of the cases for represent for how this format represents number. Notice this is my normal floating number. He's giving the cases for single precision and double precision, and then this is the meaning of these cases. All right. Notice that he's in this case here, right? This is our normal floating number. This is our normal floating number. So when the exponent goes from 1 to the maximum value minus 1, that's when I expect my floating number. The fraction can be anything, and we can compute it with the formula that we saw earlier. Okay, now, so the question is, what happens if the exponent drops less than 1, which is these cases, the exponent is a 0, right? I'm focusing on single precision, by the way. Double precision follow suit, so just larger sizes. So if the exponent is 0, we check the fraction. If the fraction is 0, it means I have the true 0. So when the exponent is 0 and the fraction is 0, I'm representing the value of 0. Okay, what happens if the exponent is 0 and I have non-zero fraction? Well, this is what we will refer to as a denormalized number, which we will explain later on. Okay, so we say that the normal range for the exponent is from 1 to max minus 1. Okay, we looked at what happened when I dropped the exponent to 0. I have two special cases for the 0 and denormalized. What happened if this exponent goes all the way to the max value, which is, in the case of single precision, 255. Okay, why 255? Because I have 8 bits, and the maximum is 2 to the power 8. Okay, 255, we will check again the fraction. If I have the maximum exponent with a 0, it means I am representing plus or minus infinity based on the sign bit. Okay, plus or minus based on the sign bit will tell me I have a plus infinity or. Okay, what about if I have a maximum exponent and a non-zero fraction? Well, in this case, this number is not a number. It means that it doesn't represent any valid number in the floating point format. So therefore, you can see how this is my normal floating point number, and the special cases when the exponent is zero, I can represent a zero or a denormalized, or in special case when I have the maximum number of the value of the exponent, I can be representing infinity or not a number. So these are the cases. Double precision follows suit as with the single precision, but with larger number. Remember, the exponent is 8 bits for single precision, 11 bits for double precision. Now, let's take a look at the range of these numbers. What do you mean by the range? Which means that if I represent the number, okay, if I represent this is the number here, the number line. So I start here with a 0, then I go all the way to the largest number here, okay, and then I have the closest number here to 0. I call it the smallest. Okay, the smallest number. So what is the smallest number close to 0, and what is the largest number that I can represent? Okay, in terms of the smallest number, the exponent will have a value of a 1, because notice here the exponent range for any floating point can go from 1 to 254. So if I have a 1 here, I have to subtract the bias. We said that once we do math calculation, we need to remove the bias, which is 127. That makes the exponent minus 126. How about the fraction? Well, the fraction can be anything, right? So since I'm looking for the smallest, I'm going to make it 0. So which means this 1 plus the fraction is 1. So now, which means the number here is 1.0 times 2 to the power of the exponent that I computed, which is equals to plus or minus 1.2 times 10 to the 10 times 10 to the minus 38. So this is the smallest number. This is the closest number that I can get. Okay, in fact, now we will talk about denormalized numbers, and denormalized numbers lives between the 0 and the smallest number. This area here, this area is the area of denormalized numbers. Okay, which is between the 0 and the smallest number. Okay, these are the denormalized numbers between the 0 and the smallest number that can be represented in the form, which is right here. Well, how about if I'm looking at the largest value? Well, in this case, the largest value I will look at for the largest exponent, which is here 254. Okay, 254. Remove the bias from it, which is 127. That gives you a value of exponents 127. So now this is the exponent 127. How about the significant? Well, the significant, I'll have the 1, and I will have the fraction all ones. This is equal almost to 2. So the number is equal to 2 times 2 to the power 127, and this becomes my largest number. Okay, that is being offered by the format. Similar discussion can be done by the double, except that now we are dealing with different numbers, all right, and different values based on, since the double precision has an exponent of 11 bits and a fraction of 54. So similar discussion here, but you can see much smaller number, much larger number, and that's why we are using the double. It offers for me larger range and a smaller precision, on the expense of what? On the expense that you need 64 bit. Okay, and that is very significant in terms of memory, in terms of area, in terms of power, in terms of energy. So use the double precision wisely because of its impact on memory and power and energy. Okay, floating point precision, I'll leave this for reading. Now let's convert now a number represented in decimal to a floating point. So let's say, for example, I need to convert this number, which is minus 0.75, okay, to a floating point, single precision and double precision. Okay, so we say that we have here to represent any number, x equals the minus 1 to the power s, that I explained earlier in the slide, times 1 plus the fraction, okay, times 2 to the power exponent minus bias. Okay, so that's what we did in an earlier slide. We explained it. Now and we said this is where the s is, this is where the fraction is, and this is where the exponent. Okay, so we need to find out the what we store in the memory in this format, which is the format for the IEEE. Okay, so obviously this number is negative, right? So this s, which is right here, equals to 1. All right, now how about this 0.75? Well, the 0.75 here is in terms of binary, it is equal to minus 0.11, but that's, I need to write it as 1 point something. To represent it as 1 point something, I write it as such. Okay, minus 1, okay, that's the sign. 1.1, that's the normalization format, times 2 to the minus 1. Okay, notice how I have to play with the exponent here, minus 1. Okay, so the fraction part is what here? Is 1. So you can see that this is the fraction part. This one is not saved in the format because it's always there. Okay, how about the exponent here? Well, the exponent is the real exponent plus the bias. What's the bias here? For single precision, 127. For double precision, it is what? It is 1023. So you add, you get 126, and this is the binary format. Okay, so now I'm ready to represent everything. This is for single precision. This is my sign bit. This is my 8-bit of exponent, right, which is coming from here, right? And this is my fraction part, okay, which is coming from here. In the exam and assignments, I would like you always to express your answer in hexadecimal. So what you do, you group these bits in 4 to convert them to hex, okay? And so you can see this is our B, this is our F, this is our 4, and the rest are zeros. Similar thing can be done for the double format. Okay, so now what we did is that we have converted, let's just see here. Okay, and now what we will do is that we will look at the case of converting from floating point to decimal. So we did in the previous exam converting from decimal to a floating point, decimal system to or fixed point system, I should say, to a floating point. So this example here, what we did, we converted this number from decimal or fixed point to the floating point format. Now, from the floating point format, given a floating point format, I need to get the value of the number. Okay, so we have agreed from a previous slide that the format is the following: is that you have the most significant bit here is the sign, and then you have the exponent, and then you have the fraction. Okay, all right. So this is a number that I might see in my assignment or the exam, and I need you to find the value of this number from get the value from the format of the floating point format. In this case, I'm giving you a single precision. Okay, so obviously this is the sign, This number is negative, and this is the fraction here. So what I say is that, well, for the fraction, obviously the significant will be 1 plus this number, which is 0 1 0 0 0 0. Okay, all right, so this is my significant now. This is the exponent. Okay, I have to remove the bias. All right, and the bias to be removed is 127, so it is 129 minus the bias, which is 127. Okay, so let's evaluate the number. Minus 1 because it's negative number. 1 plus the fraction, okay, which is right here. 2 to the 129 minus 127. And that gives me, if you do the math, minus 5. You can repeat the same exercise using double precision, okay? And it will be the same technique. You will have to take the information about the sign, the exponent, the fraction from the bits that is stored in the IEEE format. Okay. Okay. Now let's see if I have. I'm gonna stop here at this slide, and we continue the discussion later on. Thank you very much.